totally have a unicorn. All right, so today we're going to take a quick look at how to use ice tables to work out things like pH of a weak acid or other systems that might use an equilibrium that gives us an amount of material at the end of a process or when it reaches its equilibrium. Our typical method for doing that is using an ice table. So I was going to take an example today that described the action of vinegar, which has one particular acid in it we know of as acetic acid. Acetic acid has two ways you can write the formula. So we can write it more molecularly, it says it's a carbon chain, or we can write it inorganically and simply identify that it gives off a hydrogen ion. What we know about acetic acid in store containers, that's typically about 7% in a vinegar sample. So 7% of the mass is acetic acid, the rest of it is the rest of the solution. And we can actually calculate a pH for that without the need of a pH probe or any indicator test. So first thing we'd need to do is to take that vinegar and convert it back to a known amount of acetic acid in a more chemical way, by molarity. So I'm going to take this 7% vinegar by mass, and I'm just going to assume a certain minimum mass of solution. So if I had 7 grams to 100 grams, that would be my 7% by mass. We can also think of that as 70 grams per 1,000. Grams of acid per grams of solution, which is a nice simple conversion to get us into molarity, because we know 70 grams of acetic acid would have a certain molar amount associated with it. So if we added up the components of the acetic acid molecule, we get a mass that's 60.02 grams per mole. And where is that 70 grams or that certain mole percentage found? In 1,000 grams of solution, which we're going to assume is mostly water, which means purposely, by this design, 1 liter of solution. And that would leave us in a molarity of our acetic acid. So we could run that through, and there's 70 over 60, so we're going to be over a little of a mole per, oops, sorry. So you guys can run that calculation out. And so we have our molarity of our acetic acid to start. I'm going to pause it for a moment. Okay, so getting back to where we left off, let's pick up from there. We can now calculate the actual molar concentration of the acetic acid when we first deal with it, but we realize this acetic acid is going to act like a weak acid and it's going to ionize. So our general form of weak acid ionization can be written in shortcut as a protonated acid, hydrogen plus an anion, splitting into hydrogen ions and those conjugate bases, the anions of the original acid. Now, this is a weak acid equilibrium. For every unit of material that moves forward, there are some units of material that come back. So, at some point, the rate of the forward reaction, the production of these ions, will be equal to the rate of the reverse reaction, the joining of these ions back into the original acid. So to figure out what's happening when we reach equilibrium, we're going to assemble an ice table, which takes into account 3 times the initial values with an I, some amount of change with a C, and the values that we would have at equilibrium, or at the end of our process, when we see no more net changes in amounts. For the purpose of this problem, we're going to leave everything in molarity, because we're just one solution. We're not adding volume, we're not taking volume, we're not adding material from any other place. We're just dealing with the solution as it is. If we were doing this with a limiting reactant approach or some other reaction like a neutralization or a titration in which we're adding volumes, we might have to go back and do this by moles first and then account for the total volume to get us back to concentration. This one we can do direct. Worked out this calculation real quick, and that is 1.16 molar acetic acid. Now initially, our concentration of hydrogen we're going to label as a 0. It's not really 0. There are some hydrogen ions in all samples of water, but compared to the amount we're going to generate, it's practically 0. And of course, initially there are no acetic acid molecules, or sorry, no acetates present because it hasn't ionized yet. So that's our initial condition. We have the weak acid and none of the products. But we know that's got to change. This system has to go forward to make products. So there's going to be some loss of acid. Now, everything in this process is a one-to-one stoichiometry. For every acid molecule that breaks, we get one piece of hydrogen and one piece of the anion. So every time we lose a weak acid molecule, we make a hydrogen ion, plus, and we make the associated anion. So this process is going to go back and forth of these splitting and these rejoining until it establishes an equal rate of reaction in both directions. At that point, we'll be at equilibrium, and we can actually calculate the concentrations of these species in solution at that time with this expression. So we just add these columns together, the initial minus the change, the initial plus the change, and this is what we would see at equilibrium. The last piece we'll need for that then is the equilibrium constant for this acid, which is a commonly known one, and set up a quick algebraic expression to turn out values of the weak acid, its hydrogen ions, and its conjugate base anions. Alright, so we're on the home stretch. What we need to do then is figure out what the actual hydrogen ion concentration is so we can take the pH. The way we're going to do that is we're going to set up the equilibrium expression according to the law of mass action, which would be the concentration of the products divided by the concentration of the reactants. So we can set that expression up, product of the products over the product of the reactants. So H plus A minus over HA. And then we just substitute in our values. The Ka value for acetic acid is a known constant, that is 1.8 times 10 to the negative 5. It's a unitless value. It's kind of gives us a reference for how it behaves, and we can use that to compare it with other acids and bases. Do a quick substitution and rearrangement. We can then work out that. Let's see. Our x times x over 1.16 minus x is equal to 1.8 times 10 to the negative 5. So if you run all the algebra through on that, you're going to get x is actually equal to 4.57 times 10 to the negative 3. I typically don't tell people how to do algebra, but I'm assuming you guys will find a way through it. This one's a quadratic expression. There are several shortcuts on your calculators that allow you to generate that value solving for x. Now, it's very important to identify what does x specifically describe. In all these problems, we always have to stop and ask ourselves, what does x describe before we think we're done? We've developed a habit in our math classes at the moment we get this value, we think we're done. But in a chemistry course, that x value probably has a few more stages of development before our problem is actually complete, before we've gone back and addressed our original question. And in this case, our original question is, what's the pH of a vinegar solution? So that x value represents the concentration of the anion, but it also represents the concentration of the hydrogen ion. We could also use the x value to determine how much of the original acid is left over. In this case, most of it. You realize that that 4 shows up here after the 6 in the thousandths place. So most of the acetic acid is still present. So you have an acidic solution, but most of the original material is left in the original form. If we take the negative log of that, that gives us our actual hydrogen ion concentration in terms of pH. And so the negative log of 4.57 times 10 to the negative 3, well, you know it's going to be less than 3 because that's that value. When you take negative log of that and then subtract that less than 1 value from it, you're going to end up with a number greater than 2 but less than 3 as a pH value. And a calculation of that will show you that it is 2.340. When we're dealing with sig figs, I don't really count our Ka values as part of our sig figs issue. And I'll take the 3 from my earlier calculation, which gives me 3 here, which is the number of points past the decimal report in our pH value. You can check your math references on why we do it that way. And hopefully that showed up on the screen. Let me step around the front of this. And it just barely did. And that is how you use an ice table to calculate concentration of materials in an equilibrium system.